Today with this microcontroller, I'm going to generate a private Wi-Fi network. So from this magazine, I took the idea to challenge myself to build one of the systems. For this project, I will connect sensors to a microcontroller to collect and send data to a website hosted on the device. The site is accessible via its unique IP address. Welcome, and we present today the challenge of engineering, episode 0, building a Wi-Fi sensor system. So welcome guys, and in this video I'm going to focus and explain the theory behind how this system works. Okay, so in my next video I'm going to upload the tutorial and the steps you have to follow to build the system, but here we're just gonna focus in understand how the system is structured and leave with some knowledge about the microcontroller and electronic stuff. Maybe some of you got a little confused in the intro about what this video is about, but I'm gonna explain here and it's really simple. So let me explain how this system works using this diagram that I have here, and how this PR motion sensor is gonna detect some infrared signals and send it to the web server. The ESP32 is equipped with a Wi-Fi chip, which can operate in two different modes. The first one is the AP mode or access point, where the ESP32 creates its own Wi-Fi network. Devices can connect directly to this network. The second type is STA or station mode, where the ESP32 connects to an existing Wi-Fi network and essentially acts as a node or a bridge within that network. Once we have activated the desired Wi-Fi mode, the next step is to host a web server inside of the microcontroller. This web server will allow us to create and serve a custom web page that we design using HTML. To access the web page, you will need to connect the ESP32's Wi-Fi network. After connecting, you will enter the IP address assigned to the ESP32 into your web browser. The format looks something like this. Now, once the server and the web page are ready, we will write code to do two main things. First, read data from the PR motion sensor, such as detecting when motion occurs. And second of all, send this sensor data to the web page in real time. Additionally, we can make the website interactive. For example, users could send commands from the web server back to the ESP32. This is for control some sensors or devices that are connected to. In this way, we create a two-way system communication between the ESP32 and the website. Firmware PHY MAC. This is how your phone streams YouTube over the Wi-Fi, or how the smart devices that are in your home talk to the router. Let's first understand what these layers mean in simple words. So, in our system, we have the physical layer that is handling radio signals. This is gonna be in the bottom. Then we have the MAC. This means media access control layer, organizing data into different packets. And then the firmware, tying it all together, and is gonna be the top layer. So let's see how each part works. Now let's look at the physical layer. This layer is where your digital data turns into radio signals. Think of it as a translator. On one side, it receives ones and zeros from the processor. On the other side, it modulates those bits into a 2.4 GHz radio wave for the Wi-Fi. When the signals come back in, it modulates them back into digital data. In other words, the PHE handles all the low-level signals magic that makes wireless communication possible, so you can just focus on coding at a higher level. Now we're looking at the MAC layer, which stands for Media Access Control. Think of it as the traffic manager for your Wi-Fi data. Here's what it does. Organize data into packets. The MAC layer takes your raw data and packages it according to the Wi-Fi standard. This ensures every device on the network speaks the same packet language and can send or receive info without confusion. The MAC layer also supports different Wi-Fi modes. In AP, your device acts like a router. In STA mode, it connects to an existing Wi-Fi network. The MAC layer coordinates these modes so devices know who is hosting and who is joining. Ensures efficient and fair access. In a crowded network, multiple devices are trying to talk at once. The MAC layer uses algorithms like CSMA to check if the airwaves are free before transmitting. This helps minimize collisions and keeps communication running smoothly. Beyond just sending packets, the MAC layer can add encryption features like WPA2 or WPA3 to protect data. This means packets get scrambled so eavesdroppers can read them. Finally, the MAC layer is what lets you use higher level protocols like TCP or AP. That is how you can upload data to a web server and download content from the internet. The ESP32 is not just hardware, it's powered by a framework that acts as the brain for managing tasks, controlling the Wi-Fi chip, and ensuring everything runs smoothly. Let's see how it works. The official framework for the ESP32 is called ESP-DIY. It's a development toolkit that handles all the low-level communications within the Wi-Fi chip. The ESP-DIY makes it easier to connect to networks, manage higher-level protocols like HTTP and MQTT, and even deal with encryption so your data stays secure. Inside ESP-DIY is a free RTOS, a real-time operating system that is essential for multitasking. Think of it as a scheduler. It makes sure different tasks like reading sensors, running a web server, and maintaining a Wi-Fi connection all get their turn without blocking each other. For example, even if one task takes longer, free RTOS keeps the rest of the system running smoothly. In summary, the framework is what ties everything together. ESP-DIY provides the tools. Free RTOs manage multitasking, and together they ensure the Wi-Fi chip operates efficiently without interfering with your application code. This is what it makes the ESP32 so powerful for IoT, handling complexity behind the scenes while keeping your code simple. The framework interacts directly with the Wi-Fi chip in three main ways. It decides whether the ESP32 acts as a station or as an access point. It handles critical moments like connecting to a network, recovering from a dropped signals, or receiving data packets. And the framework sends HTTP requests or MQTT message through the Wi-Fi chip and process any incoming data seamlessly. So, in summary, the framework is going to coordinate the MAC layers and the physical layers. The physical layers are going to convert digital data into radio waves or radio waves into digital data. And then the MAC layer is going to take all this data and is going to put it in different packets. Okay, so then we have the framework that is going to manage multitasking and higher level protocols. And we can actually simplify these way more using just code with Wi-Fi point begin and the two. We're gonna simplify all of these, and the explanation that I did before is how the system works inside. But in code, we can go just put a Wi-Fi point begin and it's gonna start running. And yeah, so this is the way we activate the Wi-Fi and we enable the communication between the sensors and the website. Now that we understood how the Wi-Fi works, we're going to get into the hosting a web server and also sending commands from the web page to displays or sensors. It depends. So the first we have to understand is for hosting a web server, we have two types of web servers, Synchronous and Asynchronous. Okay, Synchronous is a type of web server where you can send tasks but one at a time. So the processor is gonna take one task and that's it. But with an asynchronous, we can send a task from the website to the sensor and at the same time from the sensor to the website. So we can manage multiple tasks. Now, let's get into the video and keep watching that I'm going to explain each one in a deep way to understand it better. Synchronous server process requests one at a time, meaning each new request must wait for the previous one to finish before being handled. So, the pros we can find in this type of process servers are lower memory usage. Since only one request is handled at a time, RAM usage stay minimal, making it ideal for low memory ESP32 models. Simpler to implement. The request response flow is easy to code and debug, making it great for beginners, and also less CPU overhead. The ESP32 isn't overloaded with multitasking, keeping processing simple and predictable. But we also have some cons that we have to take in consideration, like blocking execution. If one request takes too long, everything else has to wait, making it slower in high traffic situations. Also, limited scalability. It struggles when handling multiple clients at once because each request is queued sequentially, and also higher latency for real-time data. Since it serves data one request at a time, real-time updates require frequent page refresh. Another type of server we can find is Asynchronous. This server can handle multiple requests at the same time, using an event-driven approach. This makes it great for real-time applications. So, some pros we can find are no blocking execution. The ESP32 can process multiple tasks simultaneously, improving responsiveness, and also better performance for multiple clients. It can handle multiple users or devices accessing the ESP32 at once without delays, and also real-time data updates. It works well with WebSockets, allowing instant sensors data updates without needing to refresh the page. But also we're gonna have some cons, like higher memory usage. Managing multiple connections require more RAM, which can be a limitation on our smaller ESP32 models. Also, complex code. The event-driven model makes it harder to debug compared to a simple request response setup. And also the potential task conflicts. If multiple clients send conflicting commands at the same time, you need extra logic to handle them correctly. So now let's see the code and understand how this works. So first, we connect the ESP32 Wi-Fi using with the code Wi-Fi point begin SSID password. This allows our ESP32 to access a web server that other devices can access. Well, also, in this case, I'm gonna use the Asynchronous Web Server. So for the initialization, we have an Asynchronous Web Server as a code on port 80. 80 has to be the number because this is the way that the port is gonna understand it is a web server. This will let us handle multiple web requests at once. For setting up the web page, we're gonna use HTML as our code language. The code inside is index.html, and explaining is, this file contains two buttons to turn the LED on and off, and also displays real-time sensor data. We can use some JavaScript functions like sendCommand function that sends an HTTP request to the ESP32 when a button is clicked, also telling to turn the LED on or off. The other function we can use is update sensors. Fetches the latest sensor data every 2 seconds on the web page. Now let's pay attention because this is how we're gonna handling web requests like LED control and sensor data. So, for serving the web page, when a user visits the ESP32's IP address, the ESP32 responds with an HTML page. Then, for handling the LED commands, when the user clicks turn on, the browser sends a request to a LED state equal on. The ESP32 extracts the state that is there in the command, parameter and turns the LED on or off using digital write. This is some C++ code we can have. And for sending the sensor data, the sensor, as a command, reads an analog sensor value and sends it back to the web page where it updates automatically. As the last step, we're gonna run the web server. So finally, we start the web server with a server point begin. After this, the ESP32 is always listening for incoming requests from the web page. So well guys, I finished the video. I hope you enjoy what I did. I think you must notice that the English is not my first language. I'm new in this of YouTube and I'm trying to get better, make better content, and it's the first time that I'm actually exposing my face to a camera and doing this YouTube thing. I like it a lot. I hope you can subscribe to the channel, comment, and I will post a video making an intro about myself and explaining better every time my goal with this channel. I'm really nervous about how this video is gonna end. I think that I made a good job. It took me a month. I'm a college student, so I'm trying to put in showing you in the videos what I learned in school and what I learned by myself. If you have something to say that it could help me to get better on this, please tell me. I will be open mind to everything you have to say, and well, I hope you enjoy it. Subscribe to the channel. I hope you can keep watching my videos, interacting with me, and I will bring better content and better stuff to you. Just keep watching, and this is the challenge of engineering, guys. Thank you for watching.